let's go ahead and dive in. The sort of frame for today's talk is going to be this question of, does it make sense to do arithmetic on a clock? So I have a picture of a clock here, and there's 12 numbers on it. And we can start just trying to do some basic arithmetic. And we'll find that we can do arithmetic, but some stuff's going to kind of go wrong. And we'll use the stuff that goes wrong in order to kind of motivate some of the technical distinctions between rings and fields and introduce some terminology like multiplicative group and generators and roots of unity. So let's just try some basic arithmetic. Does it make sense to do 8 plus 8 on a clock? I don't have a mouse. Annoying. I'm going to have the screen be a little bit smaller. Now I think you can see my mouse, right? Is that correct?
Yes.
Great. OK, so I'm going to just do 8 plus 8 here. I'm starting at 8, and I'm just going to count 8 around the clock. 8 plus 8 is plus 1, 2, 3, 4, 5, 6, 7, 8. It looks like 8 plus 8 is 4 on the clock. Continuing forward, which now is different because I need a mouse. 8 plus 100, I'm not going to bother counting all the way around, but we can sort of make sense of, well, if I went around plus 12, I'd get back to 8. If I run around another 12, I'd get back to 8. If I run around another 12, I'd get back to 8. So I can sort of break this 8 plus 100. If I count 96 around, I'm just going to do a bunch of rotations. So 8 plus 100 will get me 8 plus 96 gets me back to 8, 8 plus 97 plus 98 plus 99 plus 100. So if you've seen modular arithmetic in any context whatsoever, which I think largely most of you probably have, this shouldn't be super familiar. All we're really doing here is arithmetic modulo 12. Oops. 5 plus 5 plus 5 plus 5 plus 5. Similarly, we could just start at 5 and start counting. So in particular, 5 plus 5 plus 5 plus 5 plus 5, well, it gives me 25. It's going to end up equaling 1. Any questions about this sort of basic idea of doing addition on the clock? Is that a hand?
No, that was an admit.
Okay, gotcha. Okay, cool. So hopefully this feels pretty clear so far. And the sort of where we go from here is, okay, I can do addition. Can I do multiplication? Can I do subtraction? Can I do division? Can I talk about squares and square roots? Like, what's the sort of boundaries of where clock arithmetic seems just as intuitive as these addition problems on the page? And where does it start to break down? So addition works, and it plays nicely with subtraction. What do I mean by plays nicely with subtraction? Looking at this equation on the page, I'd like to be able to kind of subtract 8 from both sides or subtract 6 from both sides. And I can. If I start, so looking at this first equation on the bottom here, 2 minus 6, if I start at 2 and count backwards 6, 1, 2, 3, 4, 5, 6, I get to 8. And similarly, if I start at 2 and count backwards 8, I get to 6. 2, 1, 2, 3, 4, 5, 6, 7, 8, I get to 6. So addition and subtraction on the clock work very nicely, as you would hope. Oh, I do want to... What about multiplication? Can we make sense of multiplication on the clock? Well, it's really not so bad because our notion of multiplication from childhood is repeated addition. So 5 times 5, I can just think of as 5 plus 5 plus 5 plus 5 plus 5. Maybe I said the right number of 5s there. So I can certainly do multiplication on the clock. 5 times 4, similarly, this is just 5 plus 5 plus 5 plus 5. Interestingly, it does work out that 5 times 4 is the same as 4 times 5. And at this point, we have the beginnings of a multiplication table. We have 2 kind of basic multiplication problems. We have 12 numbers, just like in elementary school, we could start filling out a multiplication table. So here's the 2 arithmetic problems that we've done so far, or the 2 multiplication problems we've done so far. 4 times 4 turns out to be itself, which is a nice kind of cool feature. If you have any 9-year-olds in your midst, you might challenge them to wonder, are there any other numbers that have the property that they're their own square? So we start to see from just playing with arithmetic on a clock, some sort of interesting questions arise. Is a number its own square is quite an interesting question from my perspective. So multiplication works. Here's the whole multiplication table. Won't bother going through and doing all 144 arithmetic questions with you. What about division? Oh, sorry, before we dive into division, let me just make a couple of comments about the multiplication table here. Multiplying by 1 works as you would expect on this clock, right? The numbers in this first row and first column of the multiplication table are exactly just multiplying by 1 doesn't change anything. We call it the multiplicative identity. It leaves things the same. And 1 is our usual multiplicative identity. We also have an additive identity, a thing that doesn't change anything when we add. 0 is our normal additive identity. On the clock, it turns out there's also a number that has this property of if you count by a certain number, you're not going to change anything. There's no 0 on our clock, but we have this number 12, and if you look at 3 plus 12, or 5 plus 12, or 7 plus 12, adding 12 really does nothing to these numbers. It's just you get to the same place. And when we multiply by 0 in normal arithmetic, in other words, when we multiply by the additive identity in normal arithmetic, multiplying by 0 sends everything to 0. And it turns out that in multiplication on the clock, multiplying by 12 sort of functions in the same way. So 12 is sort of functioning exactly like 0 here in both the additive sense and the multiplicative sense. So in practice, when we're thinking about this sort of clock arithmetic world in more formal contexts, we usually would write it as 0 through 12 rather than 1 through 12. Or sorry, 0 through 11, I should say, rather than 1 through 12. And in fact, before we move forward, I want to just rewrite the multiplication table with a 0 instead of a 12. And if I'm going to write it with a 0, I may as well sort of swap it to be in this ordering, 0 through 11, rather than 1 through 12. And I'll throw back in the sort of light blue for now. The orange things are multiplying by 0, and the blue things are multiplying by 1. And we have a sort of frame of a multiplication table on a clock. Now, I said this was a lesson about finite fields, and so far we're talking about clocks. In a minute, we'll sort of unpack why I'm not referring to this as a field and instead of referring to this as a clock. And in order to do that, let's take a look at division. But I guess I'll pause for just a moment because I've been sort of speeding through this first introduction to modular arithmetic. Anything unclear so far about the way I'm using terms like identity and this notion of addition, subtraction, and multiplication on this clock with 12 digits? I'm not following the stuff in the chat, so if there are questions in the chat, if somebody would surface them orally, that would be helpful for me. I think we're good to go. Okay, cool. So let's take a look at division. A basic division question, 8 divided by 4. What does that really mean when we ask 8 divided by 4? We're looking for a number that satisfies this equation. And you can look through the table and you can find, here's an example of a location that sort of satisfies this division question. 4 times 2 certainly still equals 8 on this clock. But 4 times 5 and 4 times 8 also equal 8. So if I try to do the arithmetic question of 8 divided by 4 on this particular clock that we're looking at, I end up sort of confused of, I don't know, 8 divided by 4 has multiple answers, it seems. And on the other hand, 1 divided by 4 doesn't have any answers at all. So we've now seen some caveats. Does it make sense to do arithmetic on this clock? The answer is yes. You can do addition, subtraction, and multiplication, but division doesn't really work here. This distinction is the distinction between a ring and a field. What we've been talking about so far is ring arithmetic. And if we want to be talking about field arithmetic, we need division to work cleanly. I won't be too specific on what I mean by cleanly, but the sorts of problems we just ran into of some division problems have multiple solutions and some division problems don't have any solution is not something that we want to have. So here's what I mean by those caveats. In fact, I have a surprise one here. 4x equals 8 has 3 solutions. 4x equals 1 has no solutions. X squared equals 1 actually has 4 solutions on this clock. So if you're finding the pacing to be a little bit slow and want an arithmetic question to pursue on the side while I'm talking, feel free to try to find the 4 values on the clock that have the property that their square is equal to 1. I want to emphasize, I guess, before I get too far into this, how like K8 friendly all of these concepts are. By the end of the talk, we're going to be getting into some stuff that's kind of like doing algebra 2 over clocks. But at this stage, this is just a new world to play with arithmetic. And if you happen to have any kids in your life that are sort of, I don't know, between the ages of know what multiplication is, but haven't yet encountered finite fields in an undergraduate mathematics class, introducing them to the idea that you can actually do arithmetic on a clock is a wildly powerful invitation to some super, super deep rabbit holes of mathematics. If we sort of like go back to that multiplication table on this particular clock, there's all sorts of patterns that kids can really find and explore and wonder about. But the question remains, how do we sort of make division actually work cleanly here? I don't like these caveats. I want the caveats to go away. And the way that we can make them go away is by looking at different size clocks. So we started with this 12-hour clock because that's the clock that we all know and use. But it turns out that if we change to a different size clock, things actually work out a lot cleaner. So prime-sized clocks in particular make fields. The 4 basic operations on this clock, if you sort of just make a multiplication table, subtraction will undo addition, as you would hope. Division will undo multiplication, as you would hope. Every number has a reciprocal. In this case, 2 times 3 is equal to 1. So 2 and 3 are each other's reciprocals. And 4 is its own reciprocal on this clock. Yep. So here's the multiplication table on this clock. I think it's relatively clear what you would need to do in order to construct the entries here. So I'm not going to spend too much time rehashing what would 3 times 3 mean on this clock. If you understand what 5 times 5 meant on the other clock, then I think it should be pretty clear what 3 times 3 means on this clock. So I have this little multiplication table off to the left. And I similarly marked it with the orange zeros are what happens when you multiply by 0, and the blue row and column there are what happens when you multiply by 1. So we have on this clock an additive identity of 0. We have a multiplicative identity of 1. And this multiplication table, I want to just sort of play with a little bit more. I want to take away the 0 for some reason that I won't say too much about. now when I look at this version of it, it sort of pops out to me as it looks like a Sudoku board. Every row and every column has exactly one copy of each element. There's no repeated numbers in any row or any column. And in fact, if I rearrange, instead of writing it as 1, 2, 3, 4, I feel like if I instead write it as 1, 3, 4, 2, then it looks not only like a Sudoku board, but it actually looks just like an addition table now. If you sort of look at the shape of an addition table, the diagonals line up in exactly the way they do here. This is not a coincidence. If I take any finite field and I remove the zeros, or take the multiplication table, I should say. If I take any multiplication table for a finite field and I remove the zeros, it's going to look like a Sudoku board. And if I can find the right way to rearrange the numbers on the top or on the edges, I can make it look like an addition table. And here's the sort of cleverness that you need in order to find the rearrangement there. It turns out that these numbers on this clock can all be seen as a power of 3. 3 to the 0th power is 1. 3 to the 1st power is 3. 3 to the 2nd power would be 9, but on a 5-hour clock, that becomes 4. And 3 cubed would be 27, but on a 5-hour clock, that becomes 2. And if I fully rearrange my multiplication table in terms of...
by the way.
Sorry, what?
There's a hand raised, by the way.
Oh, great. Yeah, let's hear the hand. Thank you, Tim. Is there a question?
Yeah, just a quick one. I'm not seeing the addition here. Could you kind of explain the addition?
Sure.
Where it's like an addition table? I'm not.
Yeah.
I mean,
Yeah, no, absolutely. Take a look at the far right column here, or the far right table, and imagine there were no 3s. Then, like the exponents that are written here, I have 3 to the 0 times 3 to the 0 is 3 to the 0, which functionally is 0 plus 0 is 0. I guess I could also, if you look at a typical addition table, these diagonals. Oh, do I have a error in my? Maybe it doesn't actually look like an addition table until I rewrite it in terms of the exponents.
Yeah, I guess I'm kind of seeing it now. Like you're saying, like, look at the diagonals. So, like, for example, you pointed it at 2, 2. So 2, 2, then diagonally makes 4, and then I guess 3, 4, but in 5 and mod 5, it is 1. I guess somewhere.
I pointed at the diagonal in the wrong table. The middle table doesn't look like an addition table. It's the far right table that looks like the addition table. And so that I apologize for misleading you in answering that question.
Okay.
But if I step back to here, the diagonals here are all actually equal to each other, right? They have a diagonal of 3s, a diagonal of 4s, a diagonal of 2s, a diagonal of 1s, a diagonal of 3s. And this really, I think here, erasing the 3s, we're literally looking at an addition table. If I erase the 3s and change the x to a plus, this table will be 100% precise. Well, up to the...
Okay, I think
the end has a little bit of wraparound issue, I guess.
I guess this makes sense because I guess in multiplication, exponent is addition. Is that kind of the point to?
Yeah, yeah. The sort of, if I'm thinking in terms of a single element, and I'm looking at powers of that element, then when I multiply them together, I essentially just add the exponents. So the kind of real trick of making finite fields feel easy is you can always find a single element to focus on and just say everything else is just some power of that element. And that element that's here, it's 3, is called a generator. So to summarize, and you ask a really good question here because the addition is a little bit hard to see initially. But the key sort of magic of finite field arithmetic is that if you think of everything in terms of a generator, then multiplication just becomes effectively adding the exponents of that generator. So this is something that is maybe a little bit, this is a pretty abstract part of this. Up until now, everything's been pretty concrete. I've been able to really explicitly show the examples here. I'm asking you to take a little bit on faith that if we took a, say, clock with 7 numbers instead of 5, that we would still be able to find some generator. And if we rearranged our multiplication table in terms of that generator, things would look essentially just the same as they do here. Is that
the generator has to be a prime number?
It's a great question. And given a particular field, the question of how to find the generator is something that I'm not going to dive into. There will be a generator in any given field. There will be several generators in any given field. The question of if you're looking at, say, the clock with 47 elements, off the top of my head, I don't have a clear answer to what's going to be the generator for that field. But it's not too hard to just kind of brute force find a generator or ask Wolfram Alpha to find a generator for you. Maybe somebody else has a clear, quick answer to if there's a quick route to finding a generator. I have a hunch the answer is use the Chinese remainder theorem.
I'm not 100% certain, but I thought it was relatively prime to the... Wait, that doesn't make sense because primes are prime. Never mind. I'm wrong. Sorry.
That's good. Thanks for trying.
Also has a hand up.
Oh, yeah.
Hi. I'm haven't played with math in a long time, so forgive me if this is a rather basic way of thinking of this. But the way that my brain keeps conceptualizing this is that this is like a base 5 system that always cycles. And so I'm just kind of understanding it as it works because you never get above 5. You don't get you don't start at then when you get to 5, you get 5 with a 1 in front of it, and then 5 with a 2 in front of it. It's just always, because it's contained that way. That's how you get this result. Is that then? And so that's why there's this. What did you call it? A determiner?
A generator.
Generator. Sorry.
Yeah. No, yeah, Chelsea, that's a great way to think of it, and definitely the thinking of this is essentially a base 5 system where we just erase the tens digits and the tens digits and the hundred, everything after the units digit gets erased is a totally valid way to think about the arithmetic we're doing. It's not quite as simple though as just because it's contained. Because if we looked at, say, a base 6 system or if we look at a base 8 system, not everything is going to have a generator. So there is an additional, the primeness here is actually significant.
Right. Okay.
But yeah, great question, Chelsea. Any other hands at the moment?
Nope.
Okay, so far, the sort of motivation has been to try to give you a concrete model for what the heck are we actually talking about when somebody says a field. And I hope now you have at least a little bit of a concrete model of someone's talking about field arithmetic. I can think about it generally, at least loosely, intuitively, I can think about it as just a clock where I'm doing arithmetic, and it's a prime-sized clock, at least for our most basic fields. I'm gonna dive back in and continue forward. Oh, we're going through this actually maybe way faster than maybe faster than we should be, maybe faster than I anticipated. But okay, so I want to just introduce a little bit more kind of formal notation, because I know that some of you are encountering finite fields in contexts where it's like reading some paper that uses notation that's confusing. So just to connect this like very hands-on model with the more abstract notation that you're going to see if you're reading any papers. This is the field of order 5. And this is a multiplication table for the field of order 5. If I remove the 0, we call this the multiplicative group of the field of order 5. And the notation for that looks generally something like this. And then this last one is a multiplication table for the multiplicative group of the field of order 5, reordered using a generator. So I'll pause if there's any more questions about that, about the notation or about the term generator. Cool. I want to not get too much into this technical notation note that I have at the bottom of this slide, but I just wanted to like briefly comment on it. And if this goes over your head, like feel free to just plug your ears for the next 30 seconds, because this is going to be more technical than necessary. The arithmetic in the field of order 5 is essentially the same thing as the arithmetic in the integers, with one additional rule. And the additional rule is that all the multiples of 5 are equal to 0. So you could actually take a regular multiplication table, even like normally a 12 by 12, but you could say take like a 50 by 50 multiplication table, and just everywhere you see a multiple of 5, replace it with 0. And effectively, you would just see a bunch of copies of this table over and over and over again. Okay. I swear that I like broke these slides up better in terms of not everything appearing at the same time. So let me step back from the concrete hands-on, how do you play with fields, and step a little bit into the like, why should I care? What are fields good for in like, why are fields used in computer contexts? And there's a few kind of really nice advantages of fields. If you are writing a typical program and are going to write division, you have to worry about your like types. If you take 2 integers and divide them, you don't get another integer. And that's kind of annoying. And that just doesn't happen here. So there's no concern about being able to do division. Similarly, if you're doing arithmetic in a typical program and you want to compute, say, like 7 to the 82nd power, you're going to have to like switch from an int to a big int, or like somehow take advantage of, or you're going to have to deal with the fact that big numbers take a lot more space to represent. And in this context where everything just wraps around, nothing takes more space to represent than anything else. So there's no overflow errors, and there's no issue about needing to allocate a different amount of memory for a large number or a small number. Does anybody actually want to add in? Is there any other reasons that people...
Paul, you have a couple questions on the chat. Do you want me to read them off for you?
I think I can pop in.
Okay, yeah, you should be able to.
Let's see. Is there any difference between finite and Galois fields? Yes. I'm not going to discuss Galois fields here. we are going to discuss a little bit about field extensions towards the end, and Galois fields are, yeah, out of scope, I think, for the initial intro. And then there, I guess, is this comment from Alexander. I thought finding a generator quick is still unknown, and you got to do some elimination method. I, again, the only time I've had to find a generator in recent experience was I was thinking about the field of order 97 and looking for a generator, and I just sort of brute forced it. I opened up Excel and I did some computations and I just found it. Obviously, that's not necessarily a practical way to work with large fields, but off the top of my head, I'm not sure what the right path to finding generators quickly is, or so. Cool. I want to take a second though. Does anybody else have reasons? I'm not particularly like fluent in software development. I wonder, I guess, whether anybody else wants to add a reason that finite fields are particularly nice in software contexts that I didn't have on this list. Okay. So we've now kind of gotten through the like K6 version of finite fields. We're going to step now into the Algebra 2 version of finite fields. So what do we try to do in Algebra 2? We typically try to solve equations. This might be more of an Algebra 1 equation, but here's something that we might wonder, is there an x that satisfies this equation? And we try to graph equations. These are, I think, the two things that students in Algebra 2 spend most of their time on, is solving equations and graphing equations. And we might wonder, does it make sense to do Algebra 2 over finite fields? Can we solve that equation, and can we graph this equation? And it turns out the answer is, yeah, we can definitely graph equations over finite fields. And sometimes we can solve equations over finite fields. In particular, the first equation that I have up there does have a solution. X equals 1 satisfies that first equation. But the second equation that I have up there, x squared equals 3, you're not going to find any solution, at least within this field, to that equation. So we'll talk a little bit more about that second equation, x squared equals 3, in a moment. But I wanted to just sort of give it some visual context for thinking about finite fields and graphing with finite fields. The basic way that students are taught to graph equations, at least in the really elementary context, is just plug in some points. If you plug in x equals 0, what do you get? If you plug in x equals 1, what do you get? If you plug in x equals 2, what do you get? There's certainly nothing stopping me from plugging in points and then plotting the points on some sort of grid. And here I have the 5 values that I could possibly plug in for x and their associated points on the graph. We might wonder, how does this compare to our sort of usual graph of 4x plus 3? Here's what our usual graph of 4x plus 3 would look like. It has slope 4. It crosses the y-axis at y equals 3. And you can think about the graph on the finite field as just sort of wrapping around. Whenever we cross 5, you sort of imagine we're playing Pac-Man, and you come out on the other side of the board back at 0. So this blue part is just a continuation of that red line, but wrapped around. So we're sort of graphing on a cylinder, it seems. Here's the sort of next few wraparounds. And in fact, this wrapping around matches up along the edge on the right and the edge on the left as well. So this really is we're graphing on a Pac-Man board. More technically, you could say we're graphing on a torus or a donut, meaning we sort of take our plane and we wrap around the top and the bottom to meet, and we wrap around the left and the right to meet, and we somehow turn our piece of paper into a donut. So equations in regular life, we graph on a flat plane. Equations on a finite field are sort of looped around with respect to the x-axis and looped around with respect to the y-axis. But we can still ask the same sorts of questions we usually can. We can ask, does it cross the x-axis? Does it have roots? So let me pause at this point and invite questions, because this is sort of a weird and abstract part to some degree. Does it feel clear? Any?
There was a hand up.
Oh, there is.
Yeah, so you said x equals to 1 works for 4x plus 3 equals to 2. Can you explain that, please?
Yeah, sure. So if I plug in x equals 1, then I get 4 times 1, which is 4. And then I add 3. And on this clock, 4 plus 3, if I start here and count around 1, 2, 3, then it works.
Yeah, I wasn't saying it's in as modular arithmetic. I just thought it was normal. Yeah, thank you. That makes sense.
Gotcha. Yeah, I'm being a little bit loose here with my use of equal signs and the just like not visually overwhelming the slides. I've made some choices to sweep some stuff under the rug. So yeah, for the rest of the conversation, we're going to be focused on the field of order 5. So all the equal signs are focused in that field. And I'll comment, you could actually solve this equation here in the sort of usual way of subtract 3 from both sides and then divide by 4 is a totally valid way to do algebra in this field. Any other questions at the moment?
I have one question.
Yeah.
Seeing this graph, does this imply that this finite field can have not only integer but some real numbers?
Yeah, you make a really good question. That's a really good question. No. So the lines here are more for giving an intuition here than for actually indicating that all of the points in between are actually, they don't exist. They're not there. So the relationship between these graphs is sort of, if you took the usual graph and then wrapped it around and then deleted everything in between the grid points.
Oh, okay, I got it. Thank you.
So yeah, this point here that's shown as like, it looks like there's a point here at 1/2, comma 0, like 1/2. Yeah, there's some fuzziness that I'm sort of trying to paint broad strokes in order to connect some intuitions that I am sort of, there's some imprecisions here, and I'm glad you pointed that out. Any other questions at the moment? There's a term that I want to just, I guess, I realized that I forgot to emphasize it when we were talking about generators, and I just want to sort of slide back to here. 3, in addition to being called a generator, I might call 3 a fourth root of unity in this context. Meaning, if I take its 4th power, I get unity 1. I get a unit. So the root of unity term, which comes up all the time in finite field conversations, a root of unity is literally just some root of 1. So it might be a square root of 1 or a cube root of 1. In this case, my generator is a 4th root of 1 or a 4th root of unity. So we've seen generators, we've seen roots of unity, we've seen the idea of a multiplicative group of a field. The one other thing that is likely coming up if you're encountering finite fields in any sort of like professional application-based contexts is this idea of field extensions. And I want to spend the next few minutes trying to motivate the idea of field extensions using this sort of equation of x squared equals 3. So x squared equals 3 doesn't have a solution on, oh, what's happening? Where am I? I jumped to the wrong slide, sorry. Here's where I want to be. X squared equals 3 doesn't have a solution in the multiplication table. There's no number that when you square it, you get 3. I can see 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 4, 4 squared is 1. There's nothing that has the property that you square it and you get to 3. But we could just make one. And this is more or less what happens in regular arithmetic too. Like at some point, you've never heard of square roots or cube roots, and you realize like, oh, wait, I can write down this equation. It's kind of annoying that it doesn't have a solution. And we just sort of invent notation for like, let's say there is some number that is the square root of 3. And we stick it in the field. What do I mean by that? Like we have our multiplication table. Let's just throw an extra element in. And we can start trying to fill out our multiplication table. Of course, root 3 times root 3 is 0. Sorry, root 3 times root 3 is 3. Root 3 times 0 is 0. I can fill in these numbers, I guess. And I might hope that I've now built a field extension. But unfortunately, I don't have a field here. I don't have, if I take 2 elements here and add them together, I'm not in my list yet. So I need to include all of the sort of things that can be built using root 3. I need to include 2 plus the square root of 3, etc. Is there a question?
There's a question.
Great.
Hey, quick question regarding a few slides ago when you were referring to 3 as a 4th root of unity. I've also heard it, but I've seen it before in textbooks referring certain elements of this group as a root of unity. Now, like also textbooks say that like under multiplication, like the roots of unity and whatever z mod z or z mod n, whatever, same n, talking about roots of unity and modulo n, they're isomorphic under multiplication. But I'm curious, why do people refer to like 3 as a root of unity? Is there any like purpose in calling it a root of unity opposed to just like 3 mod 12 and saying like, oh, it's a generator of mod 12?
Yeah. So a root of unity comes up as a useful way to talk about the idea of rotation is, I think, I see. That's the answer that comes to mind. So like it comes up primarily in the context of complex numbers. Like we think of I as a 4th root of unity is a sort of typical way to think about the complex numbers. And in that context, I can sort of think about multiplying by I as a 90-degree rotation. So when I think about roots of unity, it's kind of in order to connect this idea of rotation that I'm not managing to get too much into in this introduction.
Got you. So when you're thinking of things like relating multiplication and rotation, but under roots of unity or rotation.
Yeah, it makes it sort of just like really easy to think about the kind of symmetry structure that you're working with.
Got you.
If you're
my follow-up would be like where rotation is like useful for other applications, but I'll save that for maybe another time.
Yeah, I guess.
Or understanding like when are symmetries useful in the roots of unity opposed to like other structures.
Yeah, if you come to the session on Reed-Solomon codes, we'll certainly get into that more. Good questions. So coming back to this idea of building bigger fields or building extension fields, if I encounter an equation that doesn't have a solution, I can just sort of try to throw it in. But if I want to throw in one element, I need to also kind of deal with the consequences of that choice and throw in all the associated elements that appear. This is technically, I need to take the closure under addition and multiplication. And it turns out that I'm going to end up with 25 elements here. And the extension in more formal notation, I could call this the fields of order 5 adjoin the square root of 3. This is a sort of formal notation for a field that includes this clock, meaning it includes these 5 numbers, but it also includes a bunch of other stuff that is sort of associated with the square root of 3. So to step back a little bit, we looked at one equation that didn't have a solution. We named the solution, and then we built an extension field using that solution. I could take some other equation that doesn't have a solution and name the solution and build another extension field by including that element. Or I could take some other equation and name the solution and build an extension field in terms of that element. And it turns out that these 3 fields are going to be essentially the same. What do I mean by they're going to be essentially the same? I mean, their multiplication table is going to look like a Sudoku table. And if I rearrange it in terms of a generator, it's going to look like an addition table. So there will be a single generator in each of these groups. And by sort of thinking of it as just like, well, they're all just, it's just the generator and the powers of the generator, I can sort of think of them as equivalent. So that's the sort of rapid download to an introduction to finite fields and the terms generator and root of unity and field extension and how field extensions relate to polynomials. So to really briefly sum up the last hour, prime clocks make fields. If we take some polynomial that doesn't have a solution and throw it in, then we get a field of prime power order rather than of prime order. Fields of the same size are essentially all the same. You don't need to sort of like worry too much about if you know you're looking at a field of order 49, basically the same as all other fields of order 49. And if you write fields in terms of generators, life becomes generally easier. So maybe I hope that a decent amount of this stuck and felt useful, and you maybe feel a little bit more clear context for some of these pieces. Thanks for joining. I am going to stay on for a while, certainly for the next 7 minutes, but probably for a while after that. And maybe we can just sort of shift away from me talking at you and open up for a little bit of Q&A or discussion about what's on people's minds. So feel free to sign off if you feel like not staying for the Q&A, but if you do have things on your mind that you're either wanting to unpack a little bit better or wanting to try to connect the dots about, feel free to jump in.
I have a quick question.
Yeah.
Why would I make an extension field?
That's a really nice question. The answer that I can give in terms of risc-0 system is kind of not super. Well, I'll say this, I guess. In the context of risc-0 system, we're using the size of the field as part of our probabilistic test of that everything went right in the receipt generating process. So if I'm using a larger field, then my denominator of my probabilistic test is larger, and so I get a more effective test by using an extension field. From a pure mathematics perspective, the idea that I can find a sort of nested system of related arithmetic worlds is just sort of irresistibly compelling to try to make sense of.
Yeah, I think that
But-
makes sense. I guess the thing that led me to wonder, or your answer led me to wonder, is why not just go for the next biggest prime?
Oh,
know what I
okay,
mean?
yeah. I mean, from another perspective, it's pretty annoying that I can't solve all of my equations. So the idea of like when I find an equation that is not solvable, to just add the solution in, and then if I have some other arithmetic in the field that I care about or still want to use, it's mutually compatible. If I shifted to another field, the mapping of like, but what about all of the arithmetic? So maybe there's a situation where for the vast majority of your system, you only need to be using these 5 elements, but for one particular part, you need to be referencing the extension field. If I were to just move to a
That makes
bigger
sense.
field altogether, I would lose the sort of ability to map from the small field into the big field. Does that track?
Right. Yeah. Well, I think intuitively that makes sense. I guess I'm not very strong on this math, but that makes sense. Yeah.
Any other comments, questions?
I have one question.
Yeah.
At last point that you were building an extension field, the table wasn't forming a complete field nor multiplicative group. So I am wondering how this can be used as field.
Yeah. Let me open my screen share again. You're right that the multiplication table I made there was a sort of naive first attempt. So this, I think, is where you're looking at, right? So I was sort of just trying to motivate from a like discovery perspective. I want to add the square root of 3 to my field, so I could start like this. But this is not a field. You're absolutely right. I would need to include all of these other elements of this form. So if I were to kind of build out the full table, I would end up with a 25 by 25 multiplication table. So this was just a kind of like a naive first attempt, and I omitted the like full details of the 25 by 25 table. But you could imagine, like, I have 2 plus 4 root 3 written here. If I write, say, anything from, it's like a plus b root 3, where a and b have to be between 0 and 4.
Okay,
So
I can imagine the whole 25 by 25 table now.
And it turns out that that table will be like fully self-contained. The multiplication, everything will have a reciprocal, multiplication will undo division, and vice versa. So yeah, to build the extension field, we kind of choose one root to add, and then we take the closure under addition and multiplication. Thanks for that question. So we're doing 2 more of these this month. Wednesday, every other Wednesday this month, so the 16th and the 30th. I'll be presenting about Reed-Solomon encoding on the 16th, and Bolton will be presenting about number theoretic transforms on the 30th. Both of those are ideas that are very much built using finite fields.